I've got a good woman at home who thinks I do no wrong, but sometimes, Lord, she just ain't always around. And you know that's when I fall. Now I can't help myself at all, and I get whiskey bent and hell-bound. Play me some songs about a rambling man, put a cold one in my hand, 'cause you know I love to hear those guitar sounds. But don't you play I'm so lonesome I could cry, 'cause I'll get all balled up inside, and I'll get whiskey bent and hell-bound. Sure enough, about closing time, about stoned out of my mind, and I end up with some honky-tonk special I found. Just as sure as the morning sun comes, thinking of my sweet girl at home, and I need to get whiskey bent and hell-bound. Play me the song about a rambling man, put old Jim Beam in my hand, 'cause you know I still love to get drunk and hear country sounds. But don't play your cheating heart, 'cause that'll tear me all apart. I get whiskey bent and hell-bound. Yeah, old Hank song always make me feel down.
In this video, we're going to talk about the importance of makeup air, and we'll also talk about a few design considerations related to the exhaust stack. If we don't have good makeup air, the exhaust stack is not positioned properly, and if there's not sufficient discharge velocity from the exhaust stack, the system performance will suffer. But let's talk about makeup air first. If an exhaust system is removing the air, if it's sucking out the air, there must be replacement. If there's not air replacing the sucked out air, you end up with a negative pressure atmosphere. And if you have a negative pressure atmosphere, then the fan that's creating this negative pressure is not going to be able to move the air. So if your environmental or atmospheric air pressure in the space is low, the fan has to be lower than that. The fan may not be able to go lower than that. And that's what we're talking about when we say the system is air bound. This negative pressure interferes with the proper fan functioning. So bringing in makeup air, or having a source of makeup air, helps maintain the proper pressure differentials that are needed for the fan to work properly, and prevents the system becoming air bound. The rule of thumb, it's not a law, it's not a regulation, but the common guideline that's followed when it comes to makeup air is that the makeup air volume should be 110% of your exhaust volume. Should be the air that's coming in should be 110% of the air that's going out. If we're exhausting 1,000 cubic feet per minute, our makeup supply should be at least 1,100 cubic feet per minute. We should be bringing in at least 1,100 cubic feet per minute. Now, it can be higher than that. And it could probably, in reality, be lower. It doesn't probably get by with 105%. But 110% is the guideline that is followed when designing ventilation systems. Now, the makeup air doesn't necessarily have to be provided by a fan that's blowing air into the space. There could be enough makeup air just through the natural infiltration through the building envelope. Could be. Probably not likely, especially in tighter buildings. Now, if you're working in a common shop, steel girders, steel frame, steel exterior, steel panel exterior, no insulation. Now there you're probably going to have enough natural infiltration through the openings in the building envelope. But if it's a tight structure with insulation and I'm drawing a blank right now, the building wrap, the building paper that you'll see on the exterior of a lot of structures, they'll have the plywood sheathing, and then they'll put the wrap outside of the plywood sheathing. Then inside the plywood sheathing, they'll have insulation. I mean, if it's a well-built, tight structure, like a lot of structures are nowadays, there may not be enough natural infiltration through the building envelope. But that is a possibility. Many times it's not going to be adequate. Probably not adequate, may be a little bit strong of a statement, but many times it's not going to be adequate, just depending on natural infiltration. Now, if you're able to open a door or open a window, then you're probably good. But there are some industrial environments where there aren't doors or windows to open, or opening doors and windows could interfere with the production process. If you have a stiff breeze blowing in, contaminants from outside, let's say it's a painting operation. You have painting inside of the space. You can't open the doors and windows if painting's going on inside that space, because that's going to contaminate the finish that you're applying to whatever it is you're painting. But there are some work environments where it might be possible to just open doors and windows, and that can provide the makeup air that's needed. Another issue with opening a door or window, if it's in the summertime, you might be introducing hot air into the space. That's going to cause other problems. If it's the wintertime, you may be introducing cold air into the space. That can be problematic. Now, you can design a system, and that's what we're getting into here, that just brings in outside air. It's a ventilation system component with its own fan that blows in the makeup air, that supplies the makeup air. It could also be a system where there's a recirculation of the exhausted air, like a lot of home HVAC systems or industrial HVAC systems. There's a recirculation of exhausted air that takes place. Also, with the design system, they can be designed. It doesn't have to be an air conditioning heating system, but it could be primarily an industrial local exhaust ventilation system. But you could have heating and cooling elements that would heat or cool the makeup air that's being reintroduced into the workspace if there is the need for that. Some additional points when it comes to makeup air. According to the literature, the best designs bring in the makeup air at a height of 8 to 10 feet. You were assuming a large industrial space, like we might have in the photo here. 15, 18, 20 foot sidewalls bring in that air at a height of 8 to 10 feet. Now, if it's a more modest workspace, maybe it's conventional 8-foot ceilings. generally speaking, it's best to bring in the makeup air at approximately head height. Take the average height of the workers, bring it in at a point just above head height. But there's other considerations there as well. Some finer points that we're not getting into when it comes to the exact point or the exact height that is best for bringing in that makeup air. If you're dealing with a lot of, we'll talk about this a little bit when we talk about dilution ventilation, where we're bringing fresh air into the space to dilute contaminants. If it's a high vapor density contaminant, and we bring in air at a high point within the space, that's going to affect the mixing of the air and the movement of the airflow within the space. Same thing if it's a low vapor density, that sinks, and we bring in air at a lower point into the space. So this is a design consideration, though. Engineers need to think about, what height is the makeup air going to be reintroduced. It may even be possible to reintroduce makeup air or bring makeup air into the space through a sealing duct, through the ceiling. But another consideration on makeup air, we got to make sure that the air that we're bringing in is not contaminated. We may need to have it treated before it enters, and that the treatment may be a simple particulate filtration system, or it may be a more elaborate type of air treatment system. But we do want to make sure that we're not bringing in contaminated air. We want a clean source, ideally away from other industrial operations. And I've already mentioned HVAC systems on a smaller scale. They are a good example of what we're talking about as far as air being supplied, air being exhausted, and so on, and maintaining that proper balance within the system. And it also normally includes a filtration component as well, or an air treatment component. And it's not uncommon, maybe that's a little bit strong to say normally, but it's not uncommon for industrial systems to have separate supply fans to provide the makeup air from a clean source. Then there's the point again about we have to be careful when it comes to the temperature of the air. Temperature of the air can affect the work environment and can cause an increase in the company's heating and cooling costs. A lot of different angles to consider when putting together an industrial ventilation system, and just on the makeup air side, there are considerations to be made. Now, here is a diagram illustrating what we might commonly see in an industrial kitchen. This is the entire local exhaust ventilation system that you might see in an industrial kitchen. But what I want to point out here are the makeup air units. We have our makeup air unit located on the ceiling, bringing in fresh air from the space. Now, in this diagram, the evacuation vent or the exhaust is fairly close to the makeup air unit. So if they were in close proximity, you would want to make sure that the inlet on the makeup air unit is away from the exhaust, so that you're not bringing back in the stuff that you're exhausting from the space. Another interesting thing that you might see might be designed into an industrial ventilation system when it comes to makeup air are pressure sensors. Pressure sensors that will detect whether the balance of air pressure is what it needs to be. And if the pressure is out of balance and more air it needs to be pumped into the space, then it will automatically trigger the makeup air unit. And if the air pressure starts to get too low in the space, then the sensor will send a signal to the makeup air unit, and the makeup air unit will kick on. It's kind of like a thermostat, but it's not temperature that it's reading, it's the air pressure in the space. And that's what we're looking for in our space when it comes to makeup air is balance. Almost equivalent volumes leaving and being returned. And again, ideally we're going to have our the makeup or the return air 10% greater than the air that's being exhausted. Let's talk about some exhaust stack considerations, or the discharge. There are two particular things that need to be thought about. Exhaust velocity. If our velocity at the exhaust is not great enough, then we may not be expelling the exhaust. Also, the exhaust stack height. If the height is not if that wasn't considered and the exhaust stack is not tall enough, that could result in air being blown back into the system through the exhaust stack. The exhaust stack can become an inlet in both of those scenarios that I just mentioned. In our exhaust or discharge, this is the point where our contaminated air is discharged into the environment. It could be treated, it could be untreated. We're not concerned with that. Those thoughts right now. We're just focusing on the discharge. Low toxicity contaminants away from work areas. We want to keep the contaminated air from re-entering the work area. If not properly located with enough exhaust velocity, contaminated air can re-enter the workspaces. In terms of exhaust velocity, the velocity leaving the exhaust outlet should be 150% of the maximum reasonable wind velocity. 3,000 feet per minute is a common discharge velocity that we see in ventilation systems. This discharge velocity will effectively remove or discharge the contaminants in winds up to 23 miles per hour. And this is the formula for calculating your required exhaust velocity. Again, you're probably not going to need to do this, but it's good information to have. It's a simple formula. We have 1.5 as a constant, 60 as a constant, and we have constants here. The only thing that's not a constant, 5280 is a constant. The only thing we have that's not a constant is miles per hour. That would be our wind speed. But let's look at a quick problem, and I'm not going to make you do this on the quiz. This is just FYI. Average wind speed in an area is 15 miles per hour with frequent gusts to 30 miles per hour. What is the required exhaust velocity using the 150% rule? And we're going to use 30 miles per hour. That's the maximum reasonable wind speed. Now, of course, in a thunderstorm or severe weather, it may go beyond that 30 miles per hour. But frequent gusts, 30 miles per hour, that's going to be typical. That's what I would use when determining what my exhaust velocity needs to be. And here's our formula. Now 30 miles per hour again is kind of a worst case. Average wind speed is 15 miles per hour. But if we don't design it for 30 miles per hour, wind gusts, the frequent gusts, could blow contaminated air back into the workspace. But all we need to do is plug that 30 in, multiply, divide. 30 times 5280, there's our value. Divide this value by 60, 2640, multiply by 1.5. We need a discharge velocity of 3,960 feet per minute for this location with frequent gusts up to 30 miles per hour. Another thing about having the proper exhaust velocity, it can keep the weather out, prevent rain and or snow from entering the exhaust stack, entering your facility through the exhaust stack. The other consideration that engineers, designers should take a look at would be the exhaust stack placement and height. Especially we're talking about height here. Not so much placement as it is height. The exhaust stack must be high enough, and I'm talking about the discharge, this point here, the discharge point of your exhaust stack, must be high enough to clear what we call the wake boundary. The wake boundary is created by the building. It's air turbulence created by the natural airflow over and around the building. The formula for stack height, again, a simple formula. It gives us the height of this formula gives us the height of the wake boundary. Our stack discharge point needs to be a little bit above what we calculate using this formula. Again, everything's a constant in the formula except for a couple of measurements that we're going to enter. Again, we have height of the wake boundary. D sub S is the smaller of building height or width. D sub L is the larger of building height or width. And 0.22 is a constant. And the 0.67 and 0.33 are constants also. And here's a quick example of using the formula. A welding shop is 35 feet wide, 18 feet high, and 100 feet long. What is the exhaust stack height required to clear the wake boundary? And we're not interested in the length. It's only height or width. We have these two numbers here that we're going to be dealing with. And D sub S is going to be the smaller of these two numbers. So we plug in 18 for D sub S. 35 is the larger of width or height, so we plug in 35 for D sub L. Do the math. We end up having the height of the wake boundary at 4.86 feet. The stack height should be just greater than the 4.86 feet. Converting this into inches, the 0.86, the stack height should be greater than 4 feet 10.5 inches. All right, in the next video, go ahead and end this one here. In the next video, we're going to talk about monitoring and evaluating the performance of our local exhaust ventilation system.